everyone. Let's talk about DeepSeek-R1 models. My name is Mohammad Abul Bashar. In this talk, I will be covering DeepSeek-R1 model development approach, training process, and key findings. We know that large language models are rapidly evolving towards artificial general intelligence. One of the main reasons for such rapid development is post-processing. Post-processings are being used to improve the reasoning capabilities of large language models, to align large language models with community values and customized to specific tasks with minimal computational cost. We saw that OpenAI's 01 series advanced the reasoning capabilities significantly. They excel in reasoning tasks like mathematics, logics, and coding. However, 01 series models are huge in size. It is rumored that they use 1.7 trillion parameters. The challenge is optimizing computational resources so that the smaller models achieve results similar to those large models. To address this challenge, DeepSeek explores using pure reinforcement learning without any supervised fine-tuning. The outcome of this exploration is DeepSeek-R1 and DeepSeek-R1 models. DeepSeek-R1 models are smaller in size and they have high reasoning capabilities. The model is based on DeepSeek V3 base model. It uses reinforcement learning to improve its reasoning capabilities. DeepSeek-R1 has two models, DeepSeek-R1 and DeepSeek-R1. DeepSeek-R1 model is trained using large scale, that is thousands of steps through pure reinforcement learning without any supervised fine-tuning. This approach allows the model to explore chain of thought for solving complex problems. During the reinforcement learning, they observed that advanced reasoning capabilities evolved. It demonstrates that reasoning capabilities can be impressively improved through reinforcement learning. And those capabilities can effectively solve math, logic, and code problems. However, DeepSeek-R1 faces some challenges. For example, it gives poor readability. That is, the output produced by the DeepSeek-R1 is not very user-friendly. Another thing is language mixing. Multiple languages gets mixed together. To solve these issues, they explored another model called DeepSeek-R1. DeepSeek-R1 addresses the problem associated with DeepSeek-R0, and it further enhances reasoning capabilities of DeepSeek-R0. DeepSeek-R1 model achieves performance which is comparable to OpenAI's 01 series, like 1 to 1.7. In DeepSeek-R1, they incorporate cold start data and multi-stage fine-tuning pipeline. In the multi-stage pipeline, in the first stage, they fine-tune DeepSeek V3 base with cold start data. That is, they use the initial set of cold chain of thought data to fine-tune DeepSeek V3 base model. After that, they apply pure reinforcement learning without any supervised data in the similar way of DeepSeek-R1. After that, in step 3, they apply supervised fine-tuning where they use lots of data gathered through rejection sampling. Finally, they further apply reinforcement learning for general scenarios so that DeepSeek-R1 gets aligned with human preferences. In addition to that, they apply distillation, where the knowledge of DeepSeek-R1 was distilled into several dense models. Distilled small dense models show exceptional performance. And also, they observed that smaller models can effectively replicate the reasoning patterns of larger models. Let's talk about some building blocks of a DeepSeek-R1. The first one is DeepSeek V3 base model. DeepSeek V3 base model is a fundamental model used for DeepSeek-R1 models. It has basic features and capabilities of a large language model. The key features of this model is that it consists of 671 billion parameters with only 73 billion parameters activated for each token. This technique saves a significant computational power. The second feature is it is pre-trained on 14.8 trillion tokens. This means this model is exposed to a diverse dataset for robust performance. Then it used 128K context length. That means it can handle with 128K tokens as input. This allows the model to handle long sequence of text. There are some facts that contributed to the efficiency of DeepSeek-R1 models, or more specifically, this DeepSeek V3 base model. It uses floating point 8 weights. That means compared with traditional approach of using 32 bits, it uses only 8 bits for mixed precision. This improves efficiency and performance. Then it uses multi-head latent attention technique. This multi-head latent attention compared with multi-head attention, like traditional multi-head attention. This one focuses on compressing the key value cache into a latent vector. This reduces the memory usage significantly compared to traditional multi-head attention methods. Then it uses auxiliary loss-free load balancing. This is a strategy used to manage the distribution of computational tokens among different parts of the model, specifically in mixture of expert architecture. Finally, it uses multi-token prediction objective. Instead of predicting single token or single next token, it predicts multiple next tokens simultaneously. That further improves the computation. The next building block is chain of thought. Chain of thought involves breaking down complex problems into smaller, manageable steps. Large language models uses this technique to reason through each step and leading to more accurate and coherent answers. This chain of thought serves as a foundation for DeepSeek-R1's training. Let us give a simple example. We are given a problem of calculating total cost of 3 apples and 2 bananas. If the apple cost is $1 and banana cost is $0.50. Chain of thought will break down this problem into several components. First, it calculates the cost of 3 apples. 3 times $1 equals $3. Calculate the cost of 2 bananas. 2 times $0.50 equals $1. Then it adds the cost. $3 plus $1 equals $4. And the result is $4. The third building block is reinforcement learning. DeepSeek-R1 leverages reinforcement learning to enhance its reasoning capabilities, making it a powerful and cost-effective alternative to traditional models. How it works? It has an agent, that is the model, that interacts with the environment. The environment can be anything that can provide feedback. It can be human or a reward model. After the interaction, how the interaction happens, it takes actions, that is makes decision based on its policy. Policy means parameters or weights in the model. After that, the environment, that is the humans or reward model, responds to these actions by transitioning to new states and providing rewards. Rewards means how good or bad the action is. Finally, the agent updates its policy, that is the model weights, based on the reward received, aiming to improve its decision-making over time. Let's see this simple example here. Let's say we ask the agent to complete this sentence. This movie is dash. Then the agent or the large language model will generate the response really great. So the question plus the response will go to the reward model. This movie is really great. And based on this question and response, the reward model will provide a reward. That is an estimation of how good or bad the response is. The reward model can be human, rule, or classifier. After that, the agent will need to update its parameters or weights. To do that, it uses the reward, and also it uses some regularization techniques. One such regularization technique is scale divergence. It uses scale divergence between the reference model and the new model or the new active model. So the reference model could be initial pre-trained language model, and the active model is the model that we are updating now. So combining the distribution, weight distribution, like applying the scale divergence between the weight distribution of reference model and the active model, make sure that the new model doesn't go very far from the initial model. It prevents the model from forgetting the initial knowledge. So by combining reward and KL divergence, it calculates a loss, and based on that, it uses gradient optimization technique to update its internal weights. Now let's see DeepSeek-R1 model, how it works, and so on. So we know that reinforcement learning has shown significant effectiveness in reasoning tasks. Previous works heavily relied on supervised data, which is time intensive to gather. So to remove this problem, DeepSeek-R1 focuses on exploring the potential of large language models to develop reasoning capabilities without supervised data. The assumption is that by utilizing self-evaluation of large language models that emerge through the reinforcement learning, we'll be able to provide or improve reasoning capabilities of large language models. So DeepSeek-R1 uses a rule-based reward system. We know that the reward is the source of training signal that determine the optimization direction of reinforcement learning. Rule-based reward system of DeepSeek-R1 consists of two main types of rewards: accuracy rewards and format rewards. In the accuracy rewards, it is like it evaluates whether the response is correct or not. Based on that feedback, it will update the policy. For example, to use math problems with deterministic results, the model must provide the final answer in a specific format, for example, within a box, for reliable rule-based verification. For lead code problems, a compiler generates feedback based on predefined test cases, that is like input-output scenarios. For the format rewards, it enforces the model to place its thinking between the thinking tags. It makes sure that the thinking and the result is separated, so they don't get mixed together. They explained why they didn't use reward model for developing the DeepSeek-R1. So the reason was, if they use reward model, that can suffer from reward hacking in large-scale reinforcement learning. Also, retraining the reward model requires additional training resources. That is another problem. For the DeepSeek-R1, in the reinforcement learning, they use GRPO framework, which is a group relative policy optimization framework. This method, GRPO, removes the critic model from the system, which is typically the size of the policy model. So by removing this, it increases the computational efficiency. Rather than using critic, it utilizes group sample scores that are gathered from the generated response. So for each question, GRPO samples a group of outputs, say 0, 01, 02 up to OG from the old policy. Old policy is the policy that we use to generate this response. And then we want to update our policy, which we call new policy. It then optimizes the new policy by maximizing the following objective function. It is looks like a big equation for this objective function, but the idea behind this one is very simple. So it has two components. The second component, let's see the second component first. The second component is scale divergence between the new model and the reference model. So this one will make sure that the new model doesn't go significantly different from the reference model. That is, it will make sure that the weight distribution of reference model and the new model will be similar. So it can protect it can prevent the model from catastrophic forgetting. The first component is based on rewards. So it uses the rewards and the ratio between the new model and the old model. So instead of directly utilizing the reward, it uses the Z-score normalization of the reward. So you can see in the Z-score normalization, the mean value of the group reward is subtracted from a given reward. This will make sure that the reward will update the model only related to the mean value of the group. Another thing is the ratio between the old policy and the new policy. So this ratio will make sure that the reward utilized is relative. The reward utilization for the new policy is relative to the old policy. That means it will use a very small step related to the old policy to update the new policy. Okay, now let's see some of the experimental results from the DeepSeek-R1 So in this table 2, we can see that DeepSeek-R1, the DeepSeek-R1 0 and OpenAI 01 models comparison are given here. So we can see that DeepSeek-R1's competitive performance, both with and without majority voting. Majority voting are also known as consensus. So you can see that here. Let me use the pen. So DeepSeek-R1 gives 71% accuracy, and OpenAI 01 model gives 74% accuracy for this AMI dataset, right? So which is like they are comparable. Now, if they use majority voting, it looks like DeepSeek-R1 gives a better result, 86% accuracy compared with 83% accuracy of OpenAI 01 model. And for other datasets, you can see that the accuracy of DeepSeek-R1 and OpenAI 01 models are comparable. In this graph, this one shows how the accuracy of DeepSeek-R1 models improved over the time steps. So you can see when the reinforcement learning is applied, the DeepSeek-R1 starts with nearly 15%, and then when the model is converged, the accuracy is nearly 70%. And this accuracy is similar to OpenAI's OpenAI's 01 model. See here. If they use majority voting, then you can see the DeepSeek-R1's reasoning capabilities increase significantly. And when the model is converged, it is a little bit better than OpenAI's 01 model. Another interesting thing we can see here during the reinforcement learning, as the reinforcement iteration goes on, the response length from the language model or DeepSeek-R1 model, DeepSeek-R1 increases. That is, the length of the response becomes bigger and bigger. So this indicates that as the reinforcement learning iteration goes on, the model gives more thinking time to produce the result or the response. And this more thinking time is directly related to the accuracy of the response. Here is another interesting observation. They call it aha moment. So they explain this aha moment with one example. Say they ask the model to solve this equation, root over a minus root over a plus x equal x for when a is greater than 0. So the model responds like this. In the thinking process, it says, to solve the equation, let us start by squaring both sides. So it does the squaring the both side here. And then it says there's a rearrange to isolate the inner square root. So it does the rearranging, and then it applies uh, square again to solve the equation. At this step, it says, okay, let's re-evaluate this step by step by indicating if the correct sum can be dot dot dot. That is like there are more text actually. So it says we started with this equation. First, let's square both sides. So it does that square both sides. And then it says next, I could square both sides again then to solve the equation, right? So you can see it investigates several options to solve an equation. That shows the power of reinforcement learning to investigate and reevaluate its response through different paths. So as I mentioned, even though DeepSeek-R1 gives a very good accuracy for reasoning task, the problem is it struggles with poor readability and language mixing. So to solve this problem, they develop another model called DeepSeek-R1 model. This DeepSeek-R1 model it uses multi-step training by utilizing human-friendly cold state data and reinforcement learning. Now let's see DeepSeek-R1 model. So here is the overall workflow of DeepSeek-R1 model. It has overall 5 steps. The step 1 is initial supervised fine-tuning model. So in this step, after this DeepSeek-R10 model, they collect cold state data. So how they do it? They collect thousands of cold state data to fine-tune the DeepSeek V3 base model. They use few short prompting with a long chain of thought as an example. So they use a long chain of thought as an example in the few short prompting. Then they directly prompt the model to generate detailed answers with reflection and verification. Then they refine results through post-processing by human annotators. In the second step, they utilize rule-based reinforcement learning, which is similar to how they use reinforcement learning for DeepSeek-R10. In step 3, which is large supervised fine-tuning stage, at this step, they utilize reasoning data and non-reasoning data. To collect reasoning data, they use the converse model. So after this step 2, after the reinforcement learning through after the step 1, right? So they apply step 2 reinforcement learning. When the model is converged, then they collect data in step 3, so which is reasoning data, right? So what they do is they filter out chaotic outputs and retain only correct responses, which results in 600K reasoning related samples. Then they refine those results through post-processing and human annotators. And then they collect non-reasoning data. So the non-reasoning data comes from DeepSeek V3 data collection here, like DeepSeek V3 data collection here. So they used 600K response from this converse model. So this part, which is reasoning data, and also one portion from DeepSeek V3 data collection, which is 200K general samples. So to collect this one, what they do is they simply sub-select some of the samples that they gathered for DeepSeek V3 data collection. So after that, they fine-tune for 2 epochs using this 600 plus 200K, 600K plus 200K, so 800K data samples. And these results, so this improves their like this reasoning, like it improves human readability and some reasoning capabilities. After that, they collect some data which is related to general scenarios, and then they apply this reinforcement learning again to make sure that the model aligns to human preferences, like it doesn't violate any ethical problems and so on. So that results in DeepSeek-R1 model, this model. And after that, what they do is they use this 800K collected data as the knowledge that they gathered from the DeepSeek-R1. They use this knowledge to distill several dense models that are available as like open source and very popular in the community. So those are like distilled R1 models. So they specifically they used ON 2.5 math 1.5 billion model, ON 2.5 math 7 billion model, ON 2.5 14B 14 billion model, ON 2.5 32 billion model, Llama 3.1 8 billion model, and Llama 3.3 70 billion model to do the distillation. Now let's see some of the experimental results. You can see overall the DeepSeek-R1 does very good job. Some of the observations you can see, DeepSeek-R1 outperforms DeepSeek V3 on education-oriented benchmarks like MMLU, MMLU Pro, and GPQA Diamond datasets, especially in STEM-related questions. DeepSeek-R1 demonstrates performance comparable to OpenAI's 01 or O1 on math task and SWE verified dataset. DeepSeek-R1 excels in frames dataset, which is long context dependent question answer, and simple question answer dataset, which is factual benchmark. It provides impressive results on IF format instructions, which is and also Alpaca Eval 2.0 and Arena Hard, which is writing task and open domain question answer. And they argue that the cause of the improvement is the enhancement that occurred through large-scale reinforcement learning. Even though DeepSeek-R1 provides significantly high accuracy, it has several, like at least two main problems. The first one is it performs worse than DeepSeek V3 on Chinese simple question answer, and they think this is because they applied the safety regulation through reinforcement learning to align the model into community values. And the second thing is they think engineering related dataset performance could be improved by utilizing more reinforcement learning in that area. And here we can see the performance of distilled models. You can see overall DeepSeek distilled DeepSeek models performs significantly better than other distilled models. You can see DeepSeek-R1 distilled by Llama, distilled from Llama 70 billion dataset, Llama 70 billion model. So you can see for most of the dataset, it performs significantly better than other models. So you can see 86% for majority voting in AMI, 74% for math problems, and then 65% for GPQA Diamond, 57% for live code benchmark, and the another model, which is through distilled through QN 32 billion model, dense model. So the accuracy is 72% for any dataset for pass one, right? And yep, you can see it shows really impressive results compared with other distilled models. So we can say that distillations show us strong potential for that development, and they observe that applying reinforcement learning to the distilled models could further improve the accuracy of those models. So overall, we saw that pure reinforcement learning without any supervised fine-tuning can achieve significant accuracy for reasoning tasks. And by utilizing multi-step training through cold start data, reinforcement learning, and supervised fine-tuning can give us performance comparable to OpenAI's O1 series. And also, distinction shows us strong potential for further development. Thank you. If you have questions, you can let me know through the comments. I will try to answer those questions. Hello everyone. Let's talk about DeepSeek-R1 models. My name is Mohammad Abul Bashar. In this talk, I will be covering DeepSeek-R1 model development approach, training process, and key findings. We know that large language models are rapidly evolving towards artificial general intelligence. One of the main reasons for such rapid development is post-processing. Post-processings are being used to improve the reasoning capabilities of large language models, to align large language models with community values and customize to specific tasks with minimal computational cost. We saw that OpenAI's 01 series advanced the reasoning capabilities significantly. They excelled in reasoning tasks like mathematics, logics, and coding. However,